Let's start our day 2 of Verilog 108 day course. So today we will start with the basic concepts in Verilog. Let me take the pointer. Yeah. So our today's topic is basic concepts. So we will learn about comments, operators, and we'll see some examples, and we will see about sized and unsized numbers, and we will see about unknown and high impedance values in Verilog, and we will see about negative numbers and underscores, strings, and yeah. So these are the concepts which we will cover in this session. So if you have, please be interactive in this session, and if you have any doubts, please raise the questions by interrupting me. So let's start. So in Verilog, comments can be inserted in the code for readability and documentation. So there are two ways to write the comments. Like in C also, in C language also we have comments. Similarly in Verilog also we have the comments. So there are basically two types of comments in Verilog. There are two types of comments. This is one type of comment, and followed this is another type of comment. This is one line comment. This is one line comment, and this is used for multiple line comment. Multiple line comment. So basically these comments are used for increase the readability. For example, if we write any code, for example, we will take again our half adder example, module half adder, and we will write some code here, and we will end the module. So for increasing the readability, for example, what this module is doing, we can write a comment. For example, we can write a single line comment. This module is a half adder module. Like that, we can write a comment. So the reader who is reading our code can understand which design we are writing. So these comments are used for increasing the readability. So there are two types of comment. One is one line comment which starts with this symbol, and Verilog skips from that point to the end of the line. So the simulator will skip the execution of these comments. The one which is written inside these comments will be skipped by the simulator. And there is another type of comment which is called multiple line comments, which starts with backslash and star and ends with star and backslash. So for example, if we write backslash star, and if we write anything inside this,
Hello.
yeah,
Hello, bro. We are not able to see the screen.
not able to see screen.
We are looking to see the. Yeah, just only we are seeing the first week, not.
Wait a minute. So there are basically two types of comments. One is one line comment, which comment only a single line, and another is multiple line comment, which comment all the lines which is written inside that multiple line comment. So for example, this is a one line comment. So if we write, this is a half adder module, so this line will be commented and this will not be executed by the simulator. And if we use a multiple line comment, then the code which is written, or the information which is written inside this multiple line comment, will be skipped by the simulator. So these are the two types of comments in Verilog. So is this clear for everyone? If you have any doubts, please ask, or can we move forward? Hello.
Yeah, bro, we got it.
Yeah. So now,
What is the necessary of writing comments?
yeah, comments are basically used for increasing the readability. Like if we write a code, then we only know what that code is executing. But if any other wants to know what the
Okay.
code is executing, then for readability we can write the comment. we can explain in the form of a comment.
Okay, okay, okay.
So now operators. So operators are of three types. First one is unary operator, and second one is binary operator, and coming to third one is ternary operator. So there are three types of operators in Verilog. First one is unary, second one is binary, and third one is ternary operator. So unary operators preceded the operand. So unary operators precede the operand, and binary operators appear between the two operands, and ternary operators have two separate operators. For example, we can see here A is equal to not of B. This symbol is a complement operator. This is a complement operator. We will discuss about in our upcoming sessions. So this this is an operator and this is an operand. So A is equal to not of B. This is an operand and this is an operator. So if the operator precedes the single operand, then it is called a unary operator. Here B is the operand. And coming to binary operator, here in this second example, we can see the operator is in between the two operands. Here B and C are the operands, and our operator is separating the two operands. So this is a binary operator. And coming to ternary operator, the operator will separate the operand from other two operands. For example, here this operator is separating B from C and D. We will discuss this meaning in upcoming videos, but for now here see that this operator is differentiating this operand, that is B, from C and D. So this is a ternary operator. So these are the three types of operators in Verilog. One is unary operator, and second one is binary operator, and third one is ternary operator. We will discuss about this ternary operator, what is the meaning of this, in our upcoming sessions. So is this clear for everyone? Let's move further.
Yes, bro, got it.
Thank you. And now let's discuss about number specifications. So there are two types of number specifications in Verilog. One is sized numbers and another is unsized numbers. So what is this sized numbers? First, let's see the sized numbers. So the format for representing the sized numbers is size followed by base format followed by the number. So this is the syntax for representing the number in sized number in Verilog. What does this size specify means? It represents, wait a minute. So this size represents how many, so this size represents how many bits are present in the number. How many bits are present in the number, the size will specify. For example, if the size is 3, then the number of bits in the number is 3. So like this size will define how many bits are there in the number. And coming to the base format, we have in digital systems, we have octal, decimal, hexadecimal, and binary. So what type of number system we are using, the what type of base we are using, this base format will specify. So for octal we will use O, and for decimal we will use D, and for hexadecimal we will use H, and for binary we will use b. So like this we have to specify the base of the number. So size of the number followed by base of the number, that is octal or decimal or hexadecimal or binary, and followed by our number like 10 or 12 or some number we will use. So this is the sized numbers. So incised numbers are represented as size followed by base format followed by number. So size is written only in decimal. Yeah, here the size is only written in decimal. For example, if we want if we want the size of the number should be 4, then we should represent in only in decimal format. We cannot use hexadecimal format like a, b, etc. It should only be represented in decimal format. Here the size is written only in decimal and specifies the number of bits in the number. Here the size represents the number of bits in the number. And the legal base formats are decimal, hexadecimal, binary, and octal. Here we have discussed, right? So the base format,
Bro,
yeah,
bro, can you take an example and
yeah.
can you tell us?
Yes. We have that example in next slide. Yeah. So we have base formats like hexa, binary, and octal. Yeah, we will go to the example directly if you want. So for example, 4 tick binary 0001. So this is a sized number. Before we have discussed that here 4 represents the size, this represents the base format, and this is the number which we want to represent. So here size is 4, so the number have 4 bits, 1 2 3 4, and the base format is binary. So in binary systems we will the number should be in 0 and 1, so we are using only zeros and ones here. So this is the representation of a size number. For example, if we want to write 6 tick binary 101011, then here the size of the number is 6, that is the number consists of 6 bits, and the base format is binary followed by the number. Yeah. So if we want to represent in decimal, for example, we can write uh, here in this we can see 16 tick decimal 255. So here 16 represents the number of bits in this number. So if we convert 255 into binary, we can find 16 bits in this number. So here 16 represents the size, the number of bits in the number, and D represents the base in which the number is written, and 255 is a number. So is this clear for everyone? Are there any doubts in this topic? Hello?
Yeah, bro, got it. Yeah, got it, bro.
So please, everyone, please interact in this session. This is not a one-to-many session. This is a full duplex session. We have discussed about this in our first class also, that everyone should interact in this session so that it gives me motive to further continue the sessions. So please interact, and if you have any doubts, please ask. Okay. So let's move forward. Is it okay for everyone? Hello?
Yeah, bro, we can move for next.
Okay. Thank you. Yeah, so this is about the sized numbers. And coming to unsized numbers, so the numbers that are specified without a specification are decimal numbers by default. For example, now let's discuss about this unsized numbers. For representing this unsized numbers, in case of size numbers, we will write this format size followed by base format followed by the number. So in case of unsized numbers, we will not include this size. We will just write the base followed by the number. So if we write any number in this format, that is base followed by a number, then it is an unsized number. But the numbers that are specified without a specification are so the numbers that are written without a specification have a default number of bits, that is simulator and the machine specific. For example, if we have not mentioned any size, then it is an unsized number. So by default, according to the simulator, it will by default allocate it a size of 32-bit, or it depends upon the simulator. So the size is allocated by the simulator to this number. And if we does not specify, if we don't specify this base, then it will be by default a decimal number. For example, here in this example we can see we are just simply writing the number 2 3 4 5 6. So by default the simulator will make it as a 32-bit. So by default the size is given as 32-bit, and we have also not declared any base format. So the base format is given as decimal to this number. So by default, if in Verilog, if we write 23456 without specifying any size or base format, then the by default the simulator will allocate size to 32-bit and base to decimal. And if we mention like this tick HC3 and we have not mentioned any size, so by default the simulator will allocate the size. It is allocating 32-bit, and the base format is hexadecimal. And similarly for octal, tick O means it represents an octal number followed by the number. So this is a 32-bit octal number. So this is about the unsized numbers. So is this clear for everyone?
Yeah, it is clear.
Yeah, thank you. So now let's discuss about unknown and high impedance. X stands for unknown and Z stands for high impedance. Unknown means we cannot know whether it is 0 or 1. We will not know whether it is 0 and 1. So Verilog has two symbols for unknown and high impedance values. These values are very important for modeling real circuits. So so an unknown value is denoted by an X and a high impedance value is denoted by Z. So this is simple representation of unknown and high impedance value. For example, if we have 12 tick hexa 12 tick H 13x, so here the size is 12 and the base format is hexa, and the number we are writing is 13x. So this is a 12-bit. So in this we have 12-bit hexa number. Four least significant bits are unknown. We already know that in hexadecimal one number represents 4 bits. For example, the binary equivalent of hexadecimal number 3 is equal to 0011. So for one number, wait a minute. Yeah. So for one number, we are having 4 equivalent bits. So for this one unknown value, we have 4. So LSB represents 4 unknown bits. So this is the meaning of this number. And 6 tick hexadecimal X. So this is a 6-bit hexa number where all the 6 values are unknown. So this is the meaning of this. Yeah. Is this clear for everyone? So yeah, here an X or Z sets 4 bits for a number in the hexadecimal. So an X or Z sets 4 bits for a number in the hexadecimal base. We have seen this. For one hexadecimal number, we have 4 bits. So if there is one unknown, then it is equivalent to 4 unknown values in binary. And 3 bits for a number in octal base. For example, if we have an octal number 1, then it is if we have an octal number 8, then it is equivalent to, sorry, if we have an octal number 7, we cannot have 8 in octal. So if we have an octal number 7, then it is in binary it is equivalent to 111. So it is equivalent to 3 binary numbers. So if we have an unknown in octal number, then it is equivalent to 3 unknowns. Like this we have to examine, and 1 bit for a number in binary base. So if the most significant bit of a number is unknown or Z, the number is automatically extended to fill the most significant bits respectively with 0, X or Z. So for example, if we have 12 tick binary uh, X10, so here we have only mentioned 3 binary numbers, that is X10. The remaining 9 the remaining 9 bits will be filled by unknown by the simulator, since the MSB is unknown. If we have 12 tick binary 010 only, we have written 12 tick binary 010, then the remaining 9 bits will be filled by 0. Since the MSB is 0, the simulator will fill remaining bits by the MSB. If it is unknown, the simulator will fill the remaining bits by unknown. If it is high impedance, that is, for example, 12 tick binary Z10, here the MSB is Z, so the remaining 9 bits will be filled by Z. So this is also a very important point. This particular point will be asked in interviews also, like they will give a particular number and they will ask what is the remaining bits. So this is a very important point to remember. So is this clear for everyone?
Bro, why is it is necessary to declare unknown number?
No, no,
Is
we are not declaring. Like in some scenarios, in some real time projects, if any unknown occurs, then it will be allocated.
okay.
Like for example, if we are getting the output of a design as unknown 10, 3 tick binary, 4 tick binary unknown 0, we are not giving unknown. The design is giving an unknown bit. So for determining these values, we are using this
Okay,
technique.
okay.
Yeah.
So whenever then we are giving the input, we need to write the size numbers only with the proper bits.
Yeah, it is better to give the size numbers. If we not provide any size or base specification, then the simulator will take care of it.
Okay.
Yeah.
Got it, bro. Thank you.
And now let's discuss about negative numbers. So the negative numbers can be specified by putting a minus sign before the size for a constant number. Size constants are always positive, so it is illegal to have a minus sign between them. So for example, sorry, here it should be minus 6. So for example, minus 6 tick decimal 3. So it is, I'm very sorry, here it should be 6 bit. So this is a, so the size here is 6 bit, and the base specification is decimal, and the number is 3. So it is a 6-bit negative number stored as 2's complement of 3. So if we want to represent 3, negative 3, minus 3 using Verilog, then we have written like this. So the simulator, what it will do, it will perform 2's complement on the number 3, and it will store the 3 in 2's complement form. So like this, if we want to represent any negative number, then we will write in this format, minus 6 tick decimal 3, like this. So the simulator will perform the 2's complement on the given number, and it will store it. We cannot declare 4 tick decimal minus 2. It is illegal. 4 tick decimal minus 2, or 3 tick binary, sorry, not binary, 3 tick decimal minus 1, like this. Here, minus symbol should be in front of the size. Then only it is legal. So this is the negative number representation. Is this clear for everyone?
Bro, can you show that how that complement will take?
Yeah, in digital we have, right? So if we want to represent minus 3 in 2's complement form, we will perform 1's complement on 3. That is, first 3 should be written in binary format, that is 0 1 1. Then we have to perform 1's complement on 0 1 1, that is 1 double 0. And we have to add plus 1 to make it 2's complement, that is 1 0 1. So this is the 2's complement of the number minus 3. So this process will be there in the digital. So the simulator follow this process, and it will convert this uh, 3 into 2's complement form. Is this clear?
But now the value is 5, right?
No, no, but it is stored in 2's complement form.
Okay,
If
okay.
you want, we can discuss about this ones
Yeah,
and
bro.
2's complement tomorrow in tomorrow's session. I will give a brief intro about how to calculate this ones and 2's complement and how we are storing it.
Yeah, okay, sure, bro. Thank you.
And coming to underscore characters, so underscore is allowed anywhere in the number except for the first character. So if we have a big number, for suppose 1 2 3 4 5 6 7, like this, so we can keep an underscore in between the numbers to uh, for increasing the readability, but we cannot keep underscore in front in the starting. It is not legal. Basically, this underscores is used for increasing the readability, and it is ignored by the Verilog. And coming to strings, so string is similar to the one which is there in the C language. So string is a sequence of characters that are enclosed by double quotes. The restriction on a string is that it must be contained on a single line, that is without a carriage written. It cannot be on multiple lines. So for example, double quotes followed by all about VLSI. So this is a string. So string is nothing but sequence of multiple characters. So strings are treated as a sequence of 1 byte ASCII values. So the value of each letter is 1 byte. So this is also a very important interview question which we have to keenly remember. So the each string value is equal to 1 byte. So how many bytes are there in this string? Means 1 2 3 4 5 6 7 8 9 10 11 12. So we have 12 into 8 values in this string. Here we can see hello Verilog world. This is also a string, and double quotes A by B. This is also a string. So what is this value of the string is 8 into 3, that is equal to 24 bits. So like this we will calculate the size of the string. Is this clear for everyone? Hello.
Yes, bro, got it.
Yeah.
Yeah,
So
got it, bro.
yeah.
Yeah.
So this is about today's session. We have discussed about basic concepts like comments, operators, and number specifications, sized numbers, unsized numbers, x or z values, and we have negative numbers, underscores, strings. So we will discuss some more basic concepts in tomorrow's session. So if you have any doubts in this session or any particular thing you wanted to ask, so please ask.